Let's talk about one of the simplest dating techniques, which is the rubidium to strontium system. Okay, rubidium and strontium are elements, and some of the rubidium in nature is the isotope 87 rubidium. 87 rubidium decays, it's an unstable isotope, spontaneously to form 87 strontium, the isotope of strontium, strontium 87. So this is the decay scheme that is used. Rubidium 87 decays to strontium 87 with a half-life, an enormous half-life, which is equal to 49 billion years. That's over 10 times older than the Earth. But nonetheless, we can still use this decay scheme if a rock is sufficiently old to have produced measurable amounts of strontium 87. So we write the equation, as always, for the decay like this. We say that the daughter, let's just write it generic here, the daughter isotope equals whatever daughter was around before radioactive decay started, plus the concentration of the parent isotope times e to the lambda, t lambda is the decay constant, minus 1. So that is your radioactive decay equation, and it describes a curve. If this is time, like this, and this is the amount of daughter, it actually describes a curve that looks like this. So this value here would be the initial concentration of the daughter here, and then with time the concentration of the daughter increases as shown by the green line. So in the case of rubidium strontium, we can write that the concentration of the daughter, strontium 87, equals the initial concentration of strontium 87 that might have existed there before radioactive decay started producing more, plus the concentration of the parent, which is 87 rubidium, times e to the lambda t minus 1. Now, if we look at this equation, we notice that it's sort of in the, well, actually, let's just make a point here. Let's circle the things that we can know and measure. We can measure the concentration of strontium 87, and we can measure the concentration of rubidium 87. We know the, let's get no here, orange. We know the decay constant. And what we don't know, and I'll put those here in yellow here, we do not know the initial concentration of strontium, and we do not know the time. So in other words, there are two unknowns in one equation, okay, which means we can't uniquely solve it for both the time and the initial concentration of strontium 87 in the rock. Now, what is actually usually done, these things in red that I've circled are actually kind of hard to measure directly. It's much easier to measure ratios of isotopes. So in the case of strontium, it turns out that strontium 86 is stable. It's a stable isotope of strontium. So what we can do then is divide this entire equation here. Divide this entire equation by strontium 86, the stable isotope of strontium that doesn't change with time, right? Because it's a stable isotope, it doesn't decay. And that produces an equation that is actually the one that is used that looks like this. The ratio of 87 strontium to 86 strontium, which is relatively easy to measure, equals the ratio of 87 strontium to 86 strontium the initial ratio of the two strontium isotopes, plus the isotopic ratio of 87 rubidium to the stable isotope of strontium, 86 strontium. Once again, times, I'll put this in brackets here, e to the lambda t minus 1. This is the equation that's actually used by isotope geologists. It looks just like the other one, except that we've divided all the isotopes by the stable isotope strontium-86. And again, the reason we did that is because it's easier to measure isotopic ratios than simple pure isotopes. Once again, this has, let's once again circle the things that we can measure. We can easily measure, well, not easily, relatively easily measure these isotopic ratios in the rock. And once again, we know the value of the decay constant. What we don't know, once again, the things that are unknowns in this equation are the initial ratio of the strontium isotopes and the time. So once again, we have one equation, two unknowns. Additionally, if we sort of define these variables, let's say let this equal y, this equal b, this here equals x and y are the variables we can measure, and this over here equals m. What we have is the equation of a line. Y, remember, is equal to mx plus b. So in terms of our variables here, we could write this. Let's do it in green here. So here's our axes. The x-axis is the ratio of 87 rubidium to 86 strontium. The y-axis is the ratio of 87 strontium to 86 strontium. And what we're saying is that this equation right here, is actually the equation of a line, like this, with the y-intercept here. This is b, remember? And that is equal to the initial ratio of 87 strontium to 86 strontium. And the slope m here equal to the term in the brackets above, which was e to the lambda t minus 1. The important thing here is that the only thing unknown here is time, so the slope is proportional to the time because lambda is a constant, right? So slope is proportional to time. So in other words, if we had a different line here, this line here would be produced by a different age and a different initial ratio, right? So if I know those two things, the age and the initial ratio of strontium-87 to strontium-86, then I can uniquely describe that equation. Our problem is that one equation has two unknowns and it's insufficient to uniquely define the equation. So in other words, let me just try to explain this one more time. If I take a rock and I take, say, a mineral out of a rock or a rock, and I plot the two isotopic ratios that I can determine. So here's my 87 strontium, 86 strontium, and here's 87 rubidium to 86 rubidium. I can measure those two isotopic ratios in my rock, and if I do that, these will plot, say, right there. There's the way a rock plots. Now, my problem is with just that point is that I don't know what line this point is on. You know, it might be on a line that looks like this, or it might be on a line that looks like this. This is line. So line 2 has a steeper slope than line 1. So line 2 here is older, but had a lower initial ratio of strontium-87 to strontium-86. Line 1 represents a younger rock, so it's less old, it hasn't evolved as much, but it started out with a higher concentration of 87 strontium to strontium-86. So I don't know which of those two lines, or which, if any line, is correct. With just 1 point, that's not enough to define a line. So the solution is to look what happens if I combine two compositions that formed at exactly the same time. So here's the idea here. Now take here, this is my great idea. Take two compositions that formed at the same time. So let's actually do that now. So let's write out our two equations. Rock 1, let's do rock 1 in white, and we'll do rock 2 in yellow. So for rock 1, we can say that the initial ratio of strontium-87 to strontium-86 for rock 1 is equal to the initial ratio of strontium-87 to 86. Initial ratio for rock 1. How am I going to show that? Tell you what, let's put the 1 up here. Okay, let's put the 1 up there. Plus the ratio of rubidium-87 to strontium-86 for rock 1 times e to the lambda t minus 1. Okay, there's our decay equation for rock 1. Now rock 2, we're going to do that in yellow here, looks exactly the same except that it's in yellow and that our actually superscripts here are number 2. So what we have for rock 2, or composition 2 I should say, is that 87 strontium to 86 strontium for rock 2, that's not squared, rock 2, equals the initial ratio of 87 strontium to 86 strontium for rock 2, plus the ratio of 87 rubidium to 86 strontium for rock 2 times e to the lambda t minus 1. Now, once again, let's circle the things we can measure here. We can measure these ratios of strontium-87 to strontium-86 and rubidium-87 to strontium-86. We can do that for both rocks. And that leaves us potentially several different unknowns. Now, first of all, remember we said that these rocks, we're assuming, formed, or these compositions formed at the same time. So they formed at the same time, then this term here, t is the same and lambda is the same. So these things are actually the same. So this is one variable, the one circled in blue. Now that leaves these two other terms, which are the initial ratios of 87, 86 in rock 1 and rock 2. And here is the key point. If these rocks formed at the same time, they presumably formed from some kind of molten soup. And when different minerals were forming at that time, it's let's try to describe this graphically. That might be worth it. Okay, so let's say here we have a big pile of magma. And from this magma, two different crystals are growing. Let's say we have a crystal of, plagioclase feldspar, which is rich in rubidium, and a crystal of, let's say, magnetite, which is low in rubidium. So these two minerals are forming, and as they form, they are going to incorporate a little bit of rubidium and a little bit of strontium. This is really the key point. If these minerals, the difference between rubidium and strontium chemically is enormous. right? Rubidium is larger than strontium. It's a completely different element, and certain minerals prefer rubidium to strontium more or less than other minerals. So it's reasonable to expect, for example, that the potagioclase feldspar mineral here might, let's say, prefer rubidium more than the magnetite mineral here, which, let's say, prefers strontium. And as a result of that, what we would expect to see is that in the blue mineral here, the plagioclase feldspar, the rubidium-strontium ratio will be larger than it is in the yellow mineral. So in other words, this rubidium-strontium ratio, because that mineral prefers rubidium, will be larger than this rubidium-strontium ratio, because that mineral doesn't. In other words, the rubidium and strontium are distributed between these two minerals differently because rubidium and strontium behave different chemically. On the other hand, if we're talking about the isotopes of strontium, to a mineral that's growing and wants to grab a little bit of strontium, the difference between strontium-87 and strontium-86 is there's none. They're exactly the same thing. So there's no reason to think that although this blue mineral might prefer rubidium over strontium, it's not going to prefer strontium-87 over strontium-86 or vice versa. In other words, the distribution of strontium-87 and strontium-86 between these two growing minerals will be exactly the same. In other words, what we're saying is that the initial concentration, before we start producing more strontium-87 due to decay, the initial concentrations of strontium-87 and 86 between these two minerals, which formed at the same time, are going to be exactly the same. In other words, these two values are actually the same. So, continuing on here, our unknowns between these two equations are the time, which affects these identical terms here, right? So that term is an unknown, and the initial ratio of strontium-87 to strontium-86, which is the same in both samples. So here we have then two equations, and only two unknowns. So we can solve it. We can solve it algebraically, or we can solve it geometrically. To show you what happens geometrically here, let's revisit our graph. So here's our graph of, this is 87 rubidium to 86 strontium to 87 strontium to 86 strontium to 6. What we're saying now is if these two rocks, first of all, let's actually draw a line here. Let's let this value in blue represent the initial ratio of 87 to 86 strontium. And we're saying that these rocks, these two compositions, had to have exactly the same initial ratio of strontium-87 to strontium-86. So they both need to have plotted initially along this line. We'll come to that in a second. If we have now two compositions, here's one composition, and here's another composition. These 2 points now define a line. And that line, it's supposed to be a straight line here, will go through the initial composition. That's what I'm trying to say. They will go through this initial strontium-87-86 composition with a slope, remember, that is equal to e to the lambda t minus 1. In other words, with a slope that determines that it's proportional to its age, t. So if I know the slope, I know the age. 2 points define a slope, and therefore these 2 points determine an age. That age is called an isochron age, and this line here is called an isochron. Now quickly, let's just consider how these rocks, these compositions evolve to the point where they get here. Remember, these are the compositions they have after they've accumulated strontium-87 for some time. Now, just remember here that the decay here is 87 rubidium becoming 87 strontium. So as this decay happens, this value here will decrease, and the amount of strontium-87 here will increase. That means that as a rock ages, it will follow a path which takes it in this direction, decreasing rubidium-87, strontium-86, but increasing strontium-87, strontium-86. So in other words, the initial composition had to have lain along this line because all of the compositions had the same initial strontium-87, strontium-86 ratio. They lie along this dashed line. And as it aged, its composition followed a path on this diagram indicated by the white arrow. Similarly, these are supposed to be parallel. The other composition must have started way out here with the same strontium-87, strontium-86 ratio, but because it contained more rubidium, it produced more strontium during that time, and so its composition has moved farther on this diagram from where it initially lay and now lies over here. So these white lines then represent the evolutionary path of a composition as it evolves on this isotope diagram. The slope determined by those 2 points gives both the age of the rock, which is related to the slope through this equation, e to the lambda t minus 1, but it also gives the initial composition of 87, 86 strontium, which was present and identical in both of the compositions. That is called the rubidium-strontium isochron method.